Welcome. In this video, we're diving into one of the fundamental principles of electrical engineering, Kirchhoff's voltage law, or KVL, specifically in AC circuits. Let's summarize KVL and understand what is AC. KVL is a fundamental principle in circuit analysis. It states that in any closed loop of a circuit, the algebraic sum of all voltages is equal to zero. In simple terms, the total voltage rise must equal the total voltage drop. This works for both DC circuits with constant voltages and AC circuits with sinusoidal voltages that vary with time. AC, or alternating current, is a type of electricity where the current and voltage change direction and magnitude in a repeating wave pattern, usually as a sine wave many times per second. This back and forth motion makes AC efficient for powering homes and businesses and allows for easy change in voltage levels for various uses. Before we move on to an example, let's quickly review phasors. On the left, we have a rotating phasor diagram. The vector, indicated in blue, rotates counterclockwise around the circle with angles marked in degrees from 0, 30, 60, etc. The length of the phasor represents the magnitude of the voltage or current. This vector spins at an angular frequency which determines the AC signal oscillation speed, and its angle increases with time. On the right, the sinusoidal waveform shows how projecting the phasor's tip onto the vertical axis creates the corresponding AC signal in the time domain. The waveform equation relates to the instantaneous value of the phasor's magnitude and phase angle. As the phasor continues to rotate, the wave moves up and down smoothly, representing the AC voltage or current. In this example, to confirm KVL works in AC, we need to show that the voltages summate to zero. After solving the capacitor reactance, total impedance, and current, we can solve for the voltages of both the resistor and the capacitor. As you can probably see, the voltages across each component don't summate to zero. Why is that? This is due to the fact that we need to add the totals as phasors, not as simple numbers like a DC circuit. In AC, each voltage has a magnitude and phase angle due to the reactance from the capacitors and the inductors. This video clearly shows how the separate voltages across the resistor, capacitor, and source behave in phase form, and at any instant along the x-axis, their phasor sum is always zero. This demonstrates Kirchhoff's voltage law, which states that the sum of all voltages in a closed circuit loop equals zero. This law reflects the conservation of energy. All energy supplied by the source is absorbed or stored by components, with none lost or gained overall in an ideal circuit.